That number 8 on the pretest because I had it up on the board, but one class walked through it, the other one I didn't. Here's some of the details. It gives you the differential equation, it writes it in y prime form, and it looks like it says solve, and that might make you think separation of variables, need to multiply things through, but if you'll notice right out of the chute, this is actually already nice and separated. You only have x's over here on the right hand side, so all you have to do is get that dx over to the right hand side, integrate both sides, so that takes you to this step right here. And then I took the liberty of doing a couple things. One, if you're going to integrate this one, you want to look at the type of integral you're going to encounter. That indicates to me that u substitution isn't going to work. The minus indicates it's not going to be an arctangent or arccotangent. So what you're left with is it factorable, and can I do partial fraction decomposition? And the answer is yes. If you can make it into factors, as I've done here, then we can go about that linear factorization. So look for those clues. Can't u sub, can't do arctangent or arccotangent, so we're here stuck with this operation. You get it into the linear factors, and then you separate it out so that you have an integral of each of those individually with an unknown numerator a, b, or c. So that's the first piece. From there, what we know is that that's still supposed to be equivalent to the original expression. So what I have down here is, here's my original integral on the left, factored out and all. And then on the right-hand side is the expanded version in linear factors, numerator a, b, and c. Next thing is since they're set equal, we're going to get a common denominator on the right, set the numerators equal, and work from there. So the common denominator is going to be the product of all these denominators. They'll be the same, so it'll end up being x minus 3, x plus 3. And then that means each of these a, b, and c gets multiplied by the other denominators. So if I highlight right here, like a is going to get multiplied by x minus 3 and x plus 3. You see that right down here. Okay, and then the other, that's just to get a common denominator. Then b is going to get multiplied by x and x plus 3, so that it has the same denominator. That's the product of all three, and so on. And so what happens is they get a common denominator, and since they have on the right and left hand side of the equation the same denominator, I'm only looking at the numerators being equal. So this expression here is just the numerators equal. Underneath each would be this common denominator, x times x minus 3 times x plus 3, etc. Alright, so that's the basic idea of decomposition. So once you've set the numerators equal, then it's all the algebra of distributing, expanding, and all that. You can kind of follow those steps down below, pause this, and kind of work your way through it. But ultimately, once you get everything distributed, you collect your x squareds. So the ax squared, the bx squared, and the cx squared, you add the coefficients with a single x squared. And then you get to the bx here, and the cx, minus 3cx. The 3b and the minus 3c are the coefficients on the x term. So we put those together. And then finally the minus 9a is all that's left. So if this is equal to 3 on the left-hand side, I do not have an x squared term on the left-hand side, so you put in 0. So that's what you're seeing right here. That's the x squared term. And then the x term, 3b minus c, I don't have one of those on the left-hand side, so that's equal to 0. And then finally the negative 9a, the constant portion, that I do know has to be 3 in order for these two to be equal. So I set that equal to 3. Then that's a system of equations. These three equations for three unknowns, so if it's solvable in a system, remember the number of equations and unknowns has to match. So there's our three equations, three unknowns. The a I've got right away, negative 1/3. And then I went ahead and subbed that right in to the top equation, see right here, and went about solving a little bit. If you simplify that, I get this expression. And then setting it above what am I already, 3b minus 3c is equal to 0. That's a system of b and c variables in two equations, so I can solve for b and c. I chose to do elimination. You can choose any method you want for systems, but it seemed nice to multiply the top row by 3 and then add down, getting my b equals 1/6. And then with negative 1/3 for a and 1/6 for b, I put them in the first equation and solved for c, which is also 1/6. So in the end, if I put the a, b, and c back, what you see here, these are my expressions. Those are my three new, that's an equivalent form to my original integral, but it's something that I can integrate using log integration. So I'll put those back in very carefully into the original. And what I get is these up top here. I got them. So the first equation here, got it. And then the second one here, got it. And the third one here, got it. And I can integrate each of those separately. And I just pulled the 1/6 and 1/3 coefficients up front. I'm going to get rid of all those markings. It's a little cluttered right now. Okay, so that's that. The integrals are all nice natural logs with their coefficients. And if you remember, when you add two logs, you can make them a product. So x minus 3 times x plus 3 in a single log. So add two logs, you can just multiply their insides together. So that would make, that's where this x squared minus 9 comes from. I should go pink on that so you can see a little better. Yeah, that's where the x squared minus 9 comes from. And then the minus 1/3 ln x, I made it x to the cube root of x, and I put it in the denominator down below. Okay, so those are nice division expressions where you say if you're subtracting logs, you can make a single log and divide. If you're adding logs, make a single log and multiply. And that's a nice combination there. So that's the end of that one. Let me know if I can help you further. That's just a little doozy of an